Let's walk through the example using the guidelines mentioned and then go ahead and sketch this function. Keep in mind that we are going through many procedures from algebra and differential calculus. The first guideline is, what is the domain of this function? And if you look at the function carefully, it's actually the product of two functions. But when we talk about domains of functions, we are particularly interested in radicals and denominators, because for real numbers, we could only take the square root of 0 and positive numbers. So it makes sense to look at the radicand and set up this inequality. Notice this is a difference of two squares. A difference of two squares can be factored, and there they are. And how do we test this polynomial to be greater than or equal to 0? We actually include that polynomial and test around the x-intercepts. And in doing so, you put the x-intercepts on a number line, and then you refer back to this polynomial to pick test values and evaluate those test values into this polynomial and see if it's greater than or equal to 0. Notice p of -4 will yield a negative output, p of 0 will yield a positive output, and then p of 100 will yield a negative output. Now we want it to be positive or equal to 0, so once you realize, oh, in this open interval here, the polynomial is going to be positive, and can we equal 0? The answer is yes. We go ahead and shade in negative root 2 and positive root 2. How do we write our answer in set builder notation? There it is. It's the set of all x's such that the absolute value of x is less than the square root of 2. Or you could write it in closed interval notation. Are there any intercepts for this function? And the answer is yes. Okay. Remember, the function is up here. The first goal is to find the x-intercepts. X-intercepts occur when y equals 0. There it is. Make y to be 0 and then solve for x. You could square both sides and notice we have a polynomial in factored form right there. Then you could factor it some more. And then once again, you're solving for x. Turns out there are 3 x-intercepts. There they are. And one of them is the origin, which means the y-intercept is also the origin. Is there any symmetry? And notice in both definitions of symmetry, we always start with the observation of f of opposite of x. So you take your function and evaluate it at opposite of x and see if there is any interesting things there. And there is, actually. This is the opposite of f of x. And this statement here is actually the definition of an odd function. So once you prove that the f of the opposite of x is equal to the opposite of f of x, we conclude that the function is odd and it's symmetric about the origin. It's always one symmetry over the other, or it's not even and not odd. So when you observe f of opposite of x, you're either going to get an even function or not even, or you're going to get an odd function or not odd. In our case, we see that the function is odd and it's symmetric about the origin. We'll take advantage of this fact later on in further procedures in algebra. Are there any asymptotes? And when you're looking for asymptotes, you also look at the end behavior. I recommend that you start with the horizontal asymptotes. The horizontal asymptotes coincide with seeking the end behavior of a function. So in order to find horizontal asymptotes, you really seek the ends or the domain of that function. And so remember, the domain for this was on the closed interval from negative root 2 to root 2. And remember, to look at the end behavior or horizontal asymptotes, we have to look at the end of the domain. So we're going to approach this endpoint from the right-hand side, and then we're going to approach the other endpoint from the left-hand side. And so that's what the limit notation is saying. We analyze the end behavior in hopes that we might find a horizontal asymptote. But if you look at the end behavior here, the limit as x approaches negative root 2 from the right-hand side of this function, you have to be using your limit intuition, which means you must be 2 steps ahead. You check its form. If you check its form, you realize, oh, that is a determinate form. So if both these limits are going to exist, then that allows you to write limit laws. You could write the limit laws, and you realize the end behavior here is actually finite. Similarly, you get the right-hand side or the right endpoint end behavior, and there they are. We have found the end behavior, and the end behavior here is ordered pairs. They're really not approaching infinity or negative infinity, so that means we have actual endpoints because of the continuous function. There are no horizontal asymptotes, and there are no vertical asymptotes, because we know 0 is not an infinity or negative infinity. Are there intervals of increasing and decreasing? In other words, can you implement the first derivative test? First derivative here of this function requires a product rule, and inside that product rule, you will execute a chain rule. So you do need mastery of all your derivatives and your derivative techniques and your derivative rules. Once you have that mastered, you're going to realize you then rely on the mastery of algebra to find your critical numbers. From this expression, you're going to factor out the greatest common factor. The greatest common factor is right there. Once you factor out the greatest common factor, you have to figure out what is the factor that is left. And it turns out it is that. With algebra, you react with more factoring. Okay, we want to be able to put this in reduced factored form. So we keep factoring, and then of course, use your language of exponents to make sure you understand that this is now in the denominator. And here's your interval for your first derivative. We have a derivative in the form of a reduced fraction, a reduced factored fraction. So we first seek type 1 critical numbers, set the first derivative equal to 0, and of course, solve the equation. Turns out you end up solving this. And those are 2 critical numbers. Type 2 critical numbers require you to seek when is the first derivative undefined. So the first derivative is undefined if your denominator is 0. Set that denominator equal to 0, solve for these other critical numbers. Now it turns out these critical numbers are actually at the endpoints, so they're not critical in our specific analysis on this domain. In other words, you could actually not call those critical numbers and just concentrate on the ones that are on the interior of the domain. So these become our critical numbers and not these two. What do you do with those critical numbers? You must put them on a number line and test the first derivative. Now, which derivative did I use? I use triple star. So I always make a note of which derivative function I'm actually going to use, or which form of the first derivative I'm going to use. I'm using the one right there above. I'm going to use this factored form or reduced factored form, and that way we could find the parity of the first derivative on a specific open interval. Notice you're testing in these 3 open intervals. You must pick your own test values. All right, in this case, I picked -1 and 3/10. There's a reason for that. If you look way over here, sometimes I do a little bit of scratch work off to the side. You rarely ever have to use a calculator in calculus. That's ironic, but it's true. You rather use algebra. Use the mastery of algebra to get you this idea of, is this first derivative positive or negative? Pick your own test values. Make sure they're in the open interval indicated by the drawing of the number line. Once you figure that out, you now know when the function is actually decreasing, and you know when the function is increasing. You read that information right there, and then you read this information right here. Summarize your intervals of decreasing and increasing. Very, very important. Realize there is a change in sign. The function went down and then it went back up. So that means at c equals -1, there should be a local min. And that is what this is describing. Make sure you're able to describe the local min explicitly. And the way you do that is actually evaluate f of -1 and find the actual output, put it right there. Now the local max, from symmetry, we could actually see that the local max is actually +1. Once again, take this function value here, take that input value of 1 and put it into the function. Take this input value of 1, put it into the function f of x. If you evaluate that, you will get +1. Turns out the local min is also an absolute min, and the local max is also an absolute max. Just by analyzing the behavior of increasing and decreasing, and the fact that we're studying a closed interval. Is there concavity and inflection points? Whenever we talk about concavity or inflection points, we need the second derivative. Go back to your function, be able to find a first derivative that easily allows you to find the second derivative. In this case, I chose this form and then use the quotient rule. Master your derivative skills and master your algebra skills. Next thing you know, it's just a repetition of factoring, and hopefully when you're factoring, you are just reacting to everything. You're just reacting to the algebra. You can do this naturally and easily, and then collect like terms and write this as a fraction. Write the second derivative as a fraction. And notice you're analyzing the numerator and the denominator, just like we did earlier. We're analyzing the numerator and the denominator, and we want to know if there are any inflection points. We need the second derivative to be continuous in order to have any chance of inflection points. So that's why there is no reason to find type 2 critical numbers for the first derivative. We only need type 1, and so we set the second derivative equal to 0 and then solve for d. Once again, a lot of factoring, not a surprise. And there's 3 d values. What do we do with those d values? We once again put them on a number line. It's actually these d values right there. And we test the second derivative. Just make sure you indicate what your test values are. These are the test values I happen to choose. How do I know to choose 1 and 3/10? Because from trigonometry, you know the square root of 2 is about 1 and 4/10. So this is a trigonometry fact, and then we're using language of trigonometry to estimate 1 and 3/10, and that's the test value I chose to have. Here's a very important fact. If you look at this very, very closely, not a total surprise, this number here is greater than 5, and that will help you figure out the parity for your second derivative. negative here, positive here, negative here, positive here. That means what? That means concave down. Function is concave down. Then function is concave up. Then the function is concave down. Then the function is concave up. Is there a change in sign? And the answer is yes. So that means there's going to be 3 inflection points. So after you figure out the intervals of concavity, go ahead and find the inflection points. Inflection points are ordered pairs. So you're going to need to evaluate the function at 3 different values. Now, because there's symmetry, we only need to evaluate this one. Evaluate this one, we also get the fact that the function is odd. When we evaluate this value, we know it'll be positive. You probably could evaluate f of 0 very, very quickly. And I knew I forgot to state something. I forgot to state the inflection points. So why don't we state them in the t-chart? I'll just label it with IP here. There's an inflection point, there's an inflection point, and there's an inflection point. So I'll write it right here. The inflection points are these 3 ordered pairs. Now, putting this giant puzzle together is no easy task. I recommend that you take your pieces, take your second derivative number line test, and draw a first derivative number line test right below it. So that's what this scheme is doing. Once you draw the 2 number lines next to each other, you're going to put together the pieces of concave down and decreasing. When you put together those 2 terms, concave down and decreasing, you then get a shape of the function. And that's the shape of concave down and decreasing on this open interval. On the next open interval, we know it's going to be what? Concave up and decreasing. So there it is, concave up and decreasing. Next open interval is going to be concave up and increasing. There it is. And then next open interval is going to be concave down and increasing. You do this with every interval. The way we analyze functions is we analyze every open interval every step of the way. It is a big puzzle with lots of vocabulary. But that's what calculus and algebra is about. Even trigonometry is a giant puzzle. So you've been doing this for quite some time. We just keep working on these puzzles. We work on the mystery and we try to uncover it. Concave up and decreasing. There it is. Along the way, you should have collected a table of ordered pairs. And if you collect that table of ordered pairs, this will make sketching the function a lot easier. Do your best to scale your values. If it's not perfectly to scale, what can you write? You could write NTS, and NTS stands for not to scale.